Hey guys, welcome to Lab 2, which is all about measurements in biology. Specifically, we're going to be looking at the metric system and the different units, how to convert them, and all of that good stuff. So let's go ahead and get started. By the end of this lab today, you should know the basic metric units used to measure length, mass, volume, and temperature. You should be able to convert one metric unit to another. So you'll need to know the prefixes kilo, hecta, deca, the base unit of mass, length, volume, and temperature, deci, centi, milli, and what that means and stands for. You'll have to be able to demonstrate being able to measure length, volume, including water displacement, mass, and temperature in metric units, and then being able to identify a beaker, a dropper pipette, a graduated pipette, a pipette pump, micropipette, Erlenmeyer flask, safety goggles, graduated cylinder, test tubes, test tube rack, test tube holder, forceps, triple beam balance, thermometer, and metric ruler. If we're looking at our base units in the metric system, we also might see SI as an abbreviation for System International. That's because our metric system was standardized by the French. When we look at those base units, when we're measuring length, we measure it in a meter, and we abbreviate that with a lowercase m. When we measure mass, we do that in grams, and that is designated with a lowercase g. Volume is measured in liters with a capital L. And temperature is measured in Celsius with a degree C, meaning degrees Celsius. A little bit of background information about the metric system. It's developed by the French in the 1700s. It is a base of 10 or powers of 10. So it's really easy to use and to convert compared to our imperial system, which is a base unit of 12. And as you can imagine from way back when you were in grade school learning your times tables, units of 10 is easier to memorize and to work with than units of 12. And this metric system is used in pretty much every country in the world except the United States. But even in the United States, our engineers and scientists have to use the metric system. And so it's especially used by scientists around the world. And SI stands for, again, that System International. If we're looking at the metric system, we have some prefixes that we put onto the base unit of meter, liter, and gram to show that we've either increased or decreased from that base unit. The other way that we can show what these prefixes mean in comparison to how many base units it is to use scientific notation or exponents. So 10 raised to a power of something. And we're going to see two different methods or systems that we can use to move or convert from a unit to another unit within the metric system using these prefixes and knowing what they mean, or using this scientific notation. But we should know that our base, that's going to be our meters, liters, and grams, is representing one base unit. So it doesn't have a scientific notation with an exponent, or sometimes you might write it as 10 to the 0 power. If we increase or are increasing going up, we have decameter, for example, and that is going to be 10 meters or 10 to the first power. Hectometer or hectoliter or hectogram that is going to be 100 base units, or 10 to the second power. Then kilo or killa, like kilometer, kilometer, that is 1,000 base units, or 10 to the third power. If we're decreasing, getting smaller, we have deci, which is 1/10, or 10 to the negative 1 of the base unit. Centi is represented by a C. That's 1/100th, or 10 to the negative 2. Milli is going to be represented by a lowercase m, and that's tens, hundredths, thousandths. So 1/1000th, or 10 to the negative 3. That's really the part that you're going to sort of stop at for our conversions, but we will see micro represented by the Greek letter mu, and that's 10 to the negative 6th, and nano, and that is 10 to the negative 9th. If you look in your textbook, or on the top hat, if you don't have a physical lab manual, you will see this chart that will give you the most common units, their symbols, and what their relationship is to help you convert. There's a method that you can use with a video on the D2L if you want to make like a little bracket, and these conversion factors will help you. I personally like to use either of the two methods we go through in this PowerPoint, but if you have a different way, or those are not making sense, please feel free to use the resources on the D2L to help you with converting from different metric measurements. But this table and how to do these is very spelled out and very detailed for you in the top hat or lab manual. So let's start with the way that I think is the easiest for the kinds of conversions we will do in this course. You need to remember the order of the prefixes in order to use this method. I like the little mnemonic device, King Henry doesn't usually drink chocolate milk. And that stands for kilo, hecto, deca, the base unit, deci, centi, milli. The reason you need to memorize these in order is because we are going to use it to help us jump around on this line and know where to add zeros into our measurements as placeholders. Okay, so if you want to add on to this nano and micro, please feel free to do that. But for what we're doing, usually King Henry doesn't use chocolate milk, or doesn't usually drink chocolate milk, works perfectly. So what is this method I'm talking about? We call it the jump method or the ladder method. Basically, what you do is you will start at a certain unit. And remembering that you have your base unit. If you get smaller, that's deci, centi, milli. If you get bigger, that's deca, hecto, kilo. When you look at your starting point, maybe that's kilometers, maybe that's meters, maybe that's centimeters. You start at a starting point. Then you are going to jump or move down or up the ladder to your ending point. You then move the decimal point from wherever it is in your number you started with in the same direction as your jumps. So if we want to take something like a meter and turn it into centimeters, we would take 2 jumps. So we would add 2 decimal points to the end, or move our decimal points 2 places and add 2 zeros to the end of the number. If we want to take meter and make it into a decameter, we do 1 jump towards the left. So we would have to move our decimal place 1 point to the left. let's do an example together. We are going to start at 4 kilometers. That's my starting point. So I'm going to find 4 kilometers on my ladder or on my jump chart. I'm trying to get to meters. That's my end point, meters. How do I get there? Well, it's going to take me 1 jump to get to hecto, 1 jump to get to deca, and 1 jump to get to my base unit of 1 meter. So it takes 3 jumps in total. That means I'm going to move my decimal point that's at the end of 4 kilometers 3 places to the right and add zeros. When I do that, I will get 4, move my decimal place over, 1 jump, 2 jumps, 3 jumps. Let's make sure you guys could see it. My 4, 1 jump, 2 jump, 3 jump. And then I'm going to add zeros as my placeholders. So 4 kilometers is equal to 4,000 meters. The other way that you can do this, which is still a wonderful method, but is a little bit more advanced and a little bit more than what we do for most of our measurements, is to subtract the exponents. So instead of remembering your ladder, King Henry doesn't usually drink chocolate milk, you'll need to memorize the exponents from our table. So you're going to determine the exponents. You're going to subtract the second exponent from the first, or basically the unit you're converting it to from the unit you've converted it from. That's going to tell you how many decimal places you need to move. If the answer from your subtraction is a positive, then you're moving the decimal to the right. If the answer from your subtraction is negative, you move it to the left. So for example, 4 kilometers, how many meters is it? Well, we know that our kilometers is 10 to the third power, and we know that our meters is 10 to the 0 power, or just 1. We do 3 minus 0. That is a positive 3. So we are going to move our decimal place 3 to the right, and we get 4,000 meters. Again, both methods are explained in a lot more detail in the Top Hat lab manual. So if this is something that you need more time with or you need to read, please feel free to do that. There are also videos posted in the extra resources on the D2L, as well as just, asking me questions, and I'm happy to help. Okay, here is some practice, and we'll do some of these together, but we won't do them all together because we will have time here to pause this video before you see the answer key. But let's start with our 2,000 milligrams. And what we need to remember is our King Henry doesn't usually drink chocolate milk. And, it won't let me write. Oh, boo. So we'll remember that. And we are starting at milligrams, which is that end of chocolate milk. And we're trying to jump to grams, which is our base unit. So that's actually jumping 1, 2, 3 units backwards or to the left, right? 1, 2, 3. So that means that 2,000 milligrams is the same as 2 grams. The opposite thing here is we've got 65 grams. That's our base unit. That's usually in our mnemonic device. And we're trying to get to milligrams. So we're going to be then jumping 1, 2, 3 to the right, adding our zeros. This is a great time right here to pause the video if you're just watching the video. That way you'll be able to um, do some of these calculations before you get the answer key. So pause now. Okay, welcome back. You should have completed all of the practice problems here, and let's see how you did. So we already went through 2,000 grams and 65,000 milligrams. But let's take a look at milliliters from liters. Again, liters is our base unit. It's the usually in our chocolate milk mnemonic device, and we're going 2 milliliters. So we need to move 1, 2, 3. Our 16 centimeters to millimeters. Centimeters is just one jump, so we add a 0. 1,400 kilometers to meters. Kilometers is 1, 2, 3 jumps to our base unit, so we add 3 zeros. 198 grams to kilograms. We need to go from our base unit 3 to the left, so we're going to jump 1, 2, 3. Again, if this is something that is making sense to you, awesome. If it is something that you are needing more help with, please feel free to look at Top Hat as well as look at the extra resource videos on the D2L. So we have these base units, and now we know how to convert from them or to them, but what do they actually mean? Length is measured as the longest extent of an object from one end to the other end. The metric base unit is 1 meter. How do you measure length? Well, you'll measure it with a metric ruler. And when you look at a metric ruler, oftentimes there will be inches on one side of it. That's our imperial system that we are familiar with in the United States. And then on the other side of it is where we'll see our centimeters. And you'll see that it's split up into little dashes that represent millimeters. So they'll be from 0 to 1. There'll be these 10 little dashes representing 1 millimeter each. When you get to 1, that's the 10th. And you'll see that from 1 to 2, that there will be, again, those millimeter dash lines. When you read a ruler, you can only read up until your significant digits or how accurate you're able to read. Basically, we have this millimeter mark here. So we can say something like 6.8 centimeters. But we can't get more accurate than that because there's not more little lines. So we can't say 6.8857 centimeters. We're not able to be that accurate. So a great tip when you're making measurements is just read to the line that you can see. That's your significant digits. That's as accurate as you can be. Again, how you read it, you'll start at 0 and measure up to something like here. That's saying that you were at 6 centimeters, 6.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. When you're looking at mass, mass is the amount of matter an object has or how much space it is occupying. It's often confused with weight, but weight is actually a measurement of the gravity's impact on mass. So you will have the same mass here on Earth as you do on the moon or on Jupiter, but your weight will be different. On the moon, you will have less weight. On Jupiter, you would have more weight because the moon has less gravity than the Earth, and Jupiter has more gravity than the Earth. When we measure mass, we measure it in grams. In order to measure mass, you'll use a triple beam balance. When you put an object on it, that's going to push down on this metal plate, which is then going to raise up this little lever arm. And you can move these little sliders, and it will give you a measurement that you would read. Next is volume. Volume is the amount of space that an object has or like takes up. And we measure that in a cubic unit because it is a measurement of length times width times height. And the base unit for this is 1 liter. In order to measure volume, we have several tools. We can use a beaker, though it's not as accurate as other tools to measure volume. We can use an Erlenmeyer flask. Erlenmeyer flasks are more accurate than beakers. And then probably the most accurate for what we will be doing in our labs are our graduated cylinders. If we want to measure smaller amounts of volume of a liquid, we can use a graduated pipette. On here, these lines will tell you how much, usually in milliliters, of liquid you have. It's for smaller volumes of liquid than what you would put into an Erlenmeyer flask, a beaker, or a graduated cylinder. In order to use it, you need a pipette pump. That is actually going to be the thing that you spin the little dial to pull the liquid into the pipette. There's also these dropper pipettes that suck up an amount of liquid. It's usually marked on the plastic. These are single-use items. And then there is a micro pipette for very, very small volumes, microliters of liquid. If we were in lab in person, there would be the opportunity to practice using graduated pipettes and micro pipettes and the pipette pumps. But obviously we're not in person. So what we have here for you are a couple of videos. They're also embedded into the D2L for you to watch so that you know how to utilize both of these items. And for how to use the pipette pump, you can skip ahead to 2 minutes and 21 seconds. How you read volume measurements is a little bit different than how you read length with a ruler or even mass with a triple beam balance. When you have a liquid, it is going to stick to itself and also stick to the container that it's in. So you can't just read a straight line across. You'll actually see that there's a bend in the liquid called a meniscus. So that's the bend or curve of the liquid. When you look at the bend or curve of the liquid, you want to put the graduated cylinder, the pipette, whatever it is, on a flat surface and get eye level with the liquid. And then you can see where the bottom of it reaches. For example, here we see that there is more than 7 milliliters of water here, but it's not quite reaching 8. So if we were at eye level, that's what this is showing us, we would see that we are at about, here's 8, here's 7.9. Here's 7.8. So like 7.85 milliliters of water. Again, I can only be as accurate as my lines allow me to be, as my device allows me to measure. So I can't say that this is 7.85321 milliliters because I can only measure between uh, zero point 0.8 and 0.9. I have to estimate in between 0.8 and 0.9. So I can get 7.85. I know what you're probably thinking. Cool, cool, cool. Why does it bend like that? Well, molecules of the liquid are attracted to the molecules of the container as well as to themselves. And that's the property of cohesion and adhesion. We're very familiar with it with water, but all liquids have these properties. So it is really causing the liquid to be attracted to the sides of the container, which is what makes this bend or this meniscus. When we're measuring volume, again, we're measuring the amount of space in this object. For box shapes, it's very, very easy. You just measure the length, multiply it by the width, multiply it by the height. If we have this box here and it's 2 centimeters in length, 3 centimeters in width, and 5 centimeters in height, we'll multiply those together and get 30 cubic centimeters. The units here are cubic centimeters that we are using. If we're looking at a liquid, 1 cubic centimeter is the same as 1 milliliter of water. How did we figure this out? Well, they actually put 1 cubic centimeter into a graduated cylinder and found out that it's the same as 1 milliliter of water. It also has the same mass as 1 gram. So 1 centimeter cubed is the same as 1 milliliter, is the same as 1 gram. And you may have also heard the term cc, like in a syringe to give an injection or a shot. Those are all equal to each other, which is really important because we can convert between a liquid volume and how much mass it takes up, or how much mass something has to a liquid volume. So again, 1 centimeter cubed of water is 1 milliliter of water, is 1 gram. How does this work? What is the mass of 50 milliliters of water? Well, it's 50 grams because if 1 milliliter of water equals 1 gram, then 50 milliliters of water equals 50 grams. What is the mass of 1 liter of water? Well, we know 1 liter of water is going to be 1,000 milliliters, which means that it is 1,000 grams or 1 kilogram. This measurement kind of thing here is very important in chemistry. So if you're taking that class, this conversion will come up again and again and again, but it is still good to know for biology too. One other very useful thing with volume is something called water displacement. What if you have an object that's not a perfect square and you can't measure length times width times height? Well, we can put water into a graduated cylinder and record how much water is in there. Then we can drop an object into that graduated cylinder, and however many milliliters the volume changes, then that is the volume of that object. So for example, we have this graduated cylinder that we have filled with 4.9 milliliters of water. We then drop in our T-Rex and we see that it went from 4.9, 5, 5.1, 5.2, 5.3. So the volume increased when we put the T-Rex in. That means that our T-Rex has a volume of 0.1234, 0.4 milliliters. That change is what we measured. If you are someone who likes to do math instead of actually counting the change, you could do something like our 5.1234 minus our 4.9, and then you would get your subtraction and get your volume. When we measure temperature, we're actually measuring the amount of kinetic energies in the molecules of that substance. The metric unit that we use is degrees Celsius. On the Celsius scale, we have water freezing at 0 degrees instead of 32 like in our imperial measurement Fahrenheit scale. And water is boiling at 100 degrees Celsius, which is in Fahrenheit 212 degrees. So you can see 0 and 100 is a little bit easier than 32 and 212. When you measure temperature, you're going to measure it using a thermometer. That being said, we want to be able to convert temperatures. A nice little saying to roughly estimate temperatures is 30 is hot, 20 is nice, 10 is cold, 0 is ice. So when we look at it, something like 30 degrees Celsius is about 90, 85 degrees. So 30 is hot, 20 is nice, that's like 65, 70. 10 is cold, 40, 50, and 0 is ice. At normal pressure, that works. And it means that water is going to boil at 100 degrees Celsius, but 212 Fahrenheit. And water is going to freeze at 0 Celsius, but 32 Fahrenheit. It really sets up this scale for Celsius, being that we have really between 0 and 32. And for Fahrenheit, we have 100 to 180. This part's not that important for you to memorize or know, but it's just how we can scale it. And when we do that scaling, we come up with this equation. In order to convert Celsius to Fahrenheit, you take the degrees Celsius, multiply it by 9/5, and then add 32. 9/5 is about 1.8. So in your book, you'll see take your degrees Celsius, multiply it by 1.8, and add 32. In order to convert Fahrenheit to Celsius, you take degrees Fahrenheit, subtract 32, and multiply it by 5/9. This, of course, is a cumbersome equation to remember. If you do it enough, you will just have it in your mind. But an easier way is if you're going from Celsius to Fahrenheit, take the degrees Celsius that you're given in your problem, multiply it by 9, divide that by 5, get your answer, and add 32. Or to convert from degrees Fahrenheit to Celsius, take the degrees Fahrenheit you're given in the problem, subtract 32, multiply that by 5, get your answer, and divide by 9. So let's take a look here. Again, we can use our little saying that 30 is hot, 20 is nice, 10 is cold, 0 is ice to roughly estimate so that we know we're going in the right direction. So we're taking 26 degrees Fahrenheit and turning, or 26 degrees Celsius and turning it into Fahrenheit. So 20 is nice. That means we're going to find out it's somewhere in like the 50s, 60s, maybe. Um, if we do that, we were a little off in our estimate, but we were still pretty close. So what we do is we take Celsius to Fahrenheit. We are going to take our 26 degrees, multiply it by 9, divide that by 5, get an answer, and add 32. 26 times 9 is 234. Divide that by 5, you get 46.8, add 32, and it's about 80 degrees, 78.8. If we want to convert 98.6 degrees Fahrenheit to Celsius, we need to first take our degrees Fahrenheit, subtract 32, multiply that by 5, get an answer, and divide it by 9. So we're going to take 98.6 minus 32. That gives us 66.6. Multiply that by 5. You get 333. Divide by 9 and you get 37. Some other lab tools that you should know about. We have test tubes and a test tube rack to hold them. And we have a test tube holder. You should not be holding test tubes that you are working with by your hands. One, you're pouring chemicals into it, and if you get it on the side of the test tube, then you're touching the chemical. But also, a lot of times we're going to be putting these test tubes into hot water baths. And hot glass and cold glass look exactly the same. If you've ever done any cooking in your life, you know that a glass dish that you put in the oven and cook a casserole in looks exactly the same as the glass dish you then put in your refrigerator and when you're keeping your leftovers. So in order to not burn yourself, you'll hold onto your test tube using your test tube holder. There's also hot plates used to heat up beakers, Erlenmeyer flasks, hot water baths, whatever it might be. There are forceps in order to hold or move small items. And there are glass stirring rods used to mix chemicals. The reason they are glass is that some chemicals will react with the metal that is in metal spoons or stirring rods, but they do not react with glass. In the top hat, you will see a list of safety equipment and other parts of lab equipment you should know and what they do. There's also a Quizlet that has all of these items for you, and that will be there to help you to make sure that you understand what the objects are and what they do. Some just last second things to remember is that you should record all significant digits according to the tool you're using. That means you can only be as accurate as the item you're using to measure. If a balance reads 25.9, record that. You don't have to go 25.596327. Just record what it is saying to you. If the graduated cylinder reads 26 milliliters, cool, record that. You don't have to do 26.57 milliliters. If you are not able to make that estimation because there's not enough lines on your graduated cylinder, don't go and record it as extra. Or if a thermometer reads 21 degrees, just record that. So, what are you going to be doing today? You're going to go through this PowerPoint or watch the video if you didn't come to the actual lab class. You're going to go to Top Hat and read concepts and practice, watch all the videos, answer all the questions. You're then going to go to McGraw-Hill and do the 4 virtual labs. Then you're going to go back to Top Hat to do your post-lab questions. You're going to go through your study guide because you have a quiz due after you take Lab 2, which will cover Lab Safety, Lab 1, and Lab 2. Here's what those McGraw-Hill labs look like. This first one is on length. So you're going to be measuring the diameter and the radius of these circles using the ruler. There's one on volume where you're going to be adding liquid to a graduated cylinder and then dropping objects in to record their volume. There is weight. It's called weight, but you're looking at mass, where you're measuring out salt onto a balance or scale. And then there is temperature, where you're going to be using a thermometer to record the temperature of these different beakers of water that have been put into different conditions. Some tips and tricks for McGraw-Hill is honestly just read exactly what it wants you to do and then make sure that you do it in exactly that order. So if it says, pick up the thermometer, click the thermometer, do that first. Then it says put it into jar A, do that first. Like, it will not let you do things out of order. And that's honestly where students get stuck, is just do it exactly in the order. All right, guys. Well, thank you so much for watching. I hope that you have a wonderful rest of your day and a great time completing your labs. Have a good one. See you later.